Welcome back, everybody. Today we will be discussing Module 1-2 of our textbook. I'm going to cover part of that today, and I will have another video posted for the second half of it. And Module 1-2 is actually optical handling and positioning. So now we're going to start working a little bit with our optics. So our objectives in this, after studying this module, the student will be able to understand the nature of optical materials and their transmission and reflection characteristics as a function of wavelength. Well, you'll be able to understand the thermal, mechanical, and chemical properties of optical materials used in making optical components, and you'll be able to understand how materials are chosen for specific uses in the visible, ultraviolet, and infrared regions. Also, you'll be able to understand how single and multiple anti-reflection coatings and filters are made and used. Now, some of you may be familiar with some of these characteristics already. I don't know if there is anyone in this class that had hobbies such as photography, and lenses that we use in photography actually have all of these characteristics, and so we actually choose different lenses based on these things and what we're trying to do. Also, you'll understand the construction and use of different mountings for lenses, mirrors, and other optical components. Also, how single and multidimensional translation and rotational stages work. You'll know how to set up an optical system involving components, optical benches, and vibration-free tables. Now, we're going to go over that here, but since we're not on campus, I cannot give you optical benches and tables to work with in your house. So we'll discuss it, but you won't actually get to work with some of that. Also, you'll see how to inspect surfaces of optical elements for scratches, chips, and digs, and how to inspect optical elements for thermal and mechanical defects. We're also going to learn how to handle, clean, and store our optical elements, and also how to contact specific vendors and determine the cost of different optical materials and components. I don't know if everyone has received their lab kits yet. They were ordered 2 weeks ago, so you should be getting them now. And so when we get to the topic of setting things up and cleaning them, you can use the stuff that's in your lab kit to work on this. So what properties do our optical materials need? So I'll list some of them here, but a transparent optical medium, such as a window, prism, or a lens, requires low absorption of light while passing through it, low reflection loss of light incident on its interfaces or surfaces, low refraction of the transmitted light, or smaller refractive index, minimum distortion of light while passing through due to imperfections in the material or the surface finish. Also, if we're working with a laser, it needs a high damage threshold to laser radiation and minimal optical degradation due to temperature, water vapor, or other hostile environmental conditions. I don't know if anyone in the class has thought about even just a window like that, but think about when you are driving your car and you have either a scratched or a very dirty windshield. The light does not transmit through that as easily as if it was a clean, not scratched windshield, and it could cause issues with your visibility as you're looking out. So yeah, even a window, we have to think about its optical characteristics. So refractive index was mentioned, and it's defined as the ratio of the speed of light in a vacuum to the speed of light in a particular medium. The refractive index is a unitless quantity, and it is always greater than 1. In general, the refractive index of an optical medium decreases with the increase of wavelength. Now, if you notice, that middle bullet says that it's always greater than 1. So when you are calculating it in something like a lab or an exam for this class, keep that in mind. If your answer comes out to be less than 1, then you know that there's a mistake in your work and you have to go look and see where you made that mistake. On this slide, we have figure 2-1, which has a graph of the refractive index of several different optical materials as a function of their wavelength. The left-hand side, we see the index of refraction somewhere between 1.45 and 1.54, and then we see that we're using 3 different materials: crown glass, acrylic, and fused quartz, and on the bottom we have our wavelength. You could also see from this graph that as the wavelength gets larger, the refractive index starts to drop slightly, right? So also, there is a simple equation that can be written that relates the refractive index n to the wavelength of light in a vacuum and the wavelength of light in that medium. And that's n is equal to the wavelength of light in the vacuum divided by the wavelength of light in a medium. Now, we could actually, using the stuff we learned in Module 1, we could rewrite that and say that n is also equal to c over v, where c is the speed of light in a vacuum and v is the speed of light in the medium that we are measuring. Absorption and transmission. A beam of light that is incident on a flat, optically transparent medium is partly reflected, partly absorbed, partly scattered, and the rest is transmitted. The amount of absorption depends on the thickness of the material, the nature of the material, and the wavelength. And the equation here that we have so that we could measure this is equation 2-2 in your textbook, and it's E is equal to E0 times E to the minus alpha x. So E0 is the incident radiance, E is the transmitted irradiance, alpha is the absorption coefficient in units of reciprocal length, and x is the absorber thickness in the same units of length used in alpha. So just make sure our units are the same when we're doing that. So then I could look at transmittance, which is used to describe the percentage of light passing through the absorber, and it is given in equation 2-3, which is shown here. And I have my transmittance T is equal to E, which is the transmitted irradiance, divided by EO, which is the incident radiance, times 100%. So looking at this, the transmittance decreases with an increase of either or both alpha and x. And since my E is equal to EO, E to the minus alpha x, that decreases as alpha and x increase. The absorption coefficient alpha depends on the nature of the material and the wavelength of the light. Most of the optical glass materials transmit nearly 100% of visible light from the near ultraviolet to the near infrared range. However, transmittance generally decreases beyond these regions. The following example will show how to use equations 2-2 and 2-3 in calculating transmittance. So here I have example 1. and it tells us the absorption coefficient of a material is 4.0 per centimeter, right? If the material has a thickness of 0.1 centimeter, calculate the transmittance. So we're going to use equation 2-2, and which says that E is equal to EO times E to the minus alpha x. In this case, we could say E is equal to EO times E to the minus 4 per centimeter times 0.1 centimeter, which ends up being to the minus 4. So that tells us that E is equal to 0.67 E0. So now we'll use the transmittance equation, which is equation 2-3, and we say that T is equal to E over E0 times 100%. And in this case, we just found that E is equal to 0.67 E0. So I could say it's equal to E is 0.67 E0 over E0 times 100% gives me that it's equal to 67%. So we are transmitting 67% of the light through that medium that we have. This table, which is table 2-1 in our textbook, actually gives you absorption and transmission characteristics of some infrared transmitting materials. And what I find interesting in this is that we start with sodium chloride, and it tells us the refractive index of sodium chloride is 1.52. Now, sodium chloride is basically salt, right? Potassium bromide is below that at 1.53. Calcium fluoride is given a refractive index of 1.42. Barium fluoride is given a refractive index of 1.46. Germanium, 2.31. Gallium arsenide, 3.12. Zinc selenide, 2.40. And cadmium telluride of 2.80. Also in this table, you will see there's comments on there. So as an example for sodium chloride, the comments say it is low cost, it is hygroscopic, has high mechanical and thermal shock resistance. The term here that you may not be aware of or you may not have heard before is hygroscopic. And hygroscopic means that it readily takes up or retains moisture. So if you're thinking of using salt as a lens, you have to make sure it's in a very dry environment because it will absorb that moisture. Whereas if we go down, it tells us that calcium fluoride is insoluble in water, it is acid resistant, and it's a strong material. So again, we have to look at how these things function in the environment that we are going to be using them. As we go down the list, actually, you could see here that it says, like the cadmium telluride has a low absorption coefficient, useful for high power infrared laser windows, but it's expensive. But if you need the other characteristics, then you will pay that money to have the proper material. So now we'll speak a little about the surface reflection of ordinary light. So reflection takes place at an interface between two media due to the difference in the refractive indices. We have an equation for that, which is shown on this slide, that says R percent is equal to N1 minus N2 divided by N1 plus N2 squared times 100, where N1 and N2 are the refractive indices of the two materials. Since the ratio in brackets is squared, it does not matter which medium we label N1 and which we label N2. Each one of these will give us the same result for R and percentage. And also this means that the reflection at the interface is the same whether the light strikes going from medium N1 to medium N2 or from N2 to N1. So what that's trying to say is that means that if I have light, let's say, going from air to glass, my R percentage will be the same if it's going from air to glass or glass to air. And this equation assumes that the light is actually perpendicular to the surface of the interface, which means it's at a 90-degree angle. And I'm going to follow in the next two slides. We have two examples, and we'll see how we calculate this. So in this figure 2.4 from our textbook, we see that we have our incident ray, which is going through air, which has a index of refraction of 1, and then it hits glass, which has the index of refraction of 1.5. And again, you could see that it's at a 90-degree angle. So we will use another equation, which is equation 2.5 in our textbook, to find our reflected light. And that equation is my R total is equal to 1 minus 2 NR divided by NR squared plus 1, where my reflection total is the total reflection, and NR is equal to NW over N of the medium. NW is the refractive index for the window, and medium is the refractive index for the medium surrounding the window. So for any optical window, neglecting absorption and scattering, the T total plus R total is equal to 1. So example 2, which we're going to get to in a minute, shows how to calculate the total reflection for a window of index N equals 1.6 situated in air, N equals 1. So in this figure, we say the incident ray is 100%, and it's saying that our transmitted ray is 96%, which means that our reflected ray is 4%, because they have to add up to the 100%. In this example, we have an optical window with an index N equals to 1.6, and it's located in air, and we're going to use N equals 1 for the air. The light is incident on the window at an angle of incidence equal to 90 degrees, which is perpendicular, and we're being asked to find the reflection total, the total reflection, right? So the figure on the lower left shows the incident light, and it shows it going through the window, and then some reflects back and some continues on through. So to find my R total, I'm going to use that equation of 1 minus 2 times NR divided by NR squared plus 1. And we know that NR is equal to N of my window divided by N of my medium. In this case, 1.6 divided by 1 is equal to 1.6. So my R total is equal to 1 minus 2 times 1.6 divided by 1.6 squared plus 1, which is equal to 0.1 or 10%. So what that is telling us is that 90% of the light is going through the medium and the other 10% is reflected back. We will now discuss how surface reflections of polarized light work. So first we'll consider unpolarized light to be incident on an interface with equal amounts of ETE and ETM. And if you don't remember from Module 1 what that stands for, the TE is transverse electric and the TM is transverse magnetic. So the electric field vibration ETE, represented by a dot, and the drawing will be on the next slide, is oriented in a direction totally perpendicular to the plane of incidence and the light ray. The electric field vibration ETM, represented by a double-headed arrow, is also totally perpendicular to the direction of the light ray, but lies in the plane of incidence. At a specific angle of incidence called the Brewster angle, the reflected light will have only the E field vibration ETE, which are the dots. The refracted beam will have all of the ETM vibration arrows, but less of the ETE vibration, since some have gone off in the reflected beam. Thus, the light in the reflected beam, around 15% of the incident light on an air-glass interface, is completely polarized with the ETM vibration. So here you'll see we have an incident light that's unpolarized, and again, as it said in the previous slide, equal amounts of ETE and ETM. I have it at angle theta, and I'm shining the light against glass, and then it gets reflected, and as it's reflected, I have ETE is what's coming through on the reflected side. But you can see the refracted beam is unpolarized. So the next page will show figure 2.6 from our textbook, and it shows a beam of polarized light, which is totally ETM, incident on a Brewster window at Brewster's angle beta. Since the electric field vibration is all ETM, there can be no reflected light. If there were, the vibration would have to be longitudinal. That is only the direction of the reflected ray. But light, which is an electromagnetic wave, contains only transverse vibrations. That is, vibrations perpendicular to the ray direction. Thus, at the Brewster's angle, there is no reflected light, only refracted light, and the refracted light is totally of polarization ETM. So here is that figure, and you can see it's showing us that we have an incident ray. It's at the Brewster angle, and it's telling us that there is no reflection if the incident light is polarized and totally ETM, and we have our transmitted ray as it goes through the glass. So the value for the Brewster angle can be calculated with the simple formula, which is equation 2-6 in our text, which is theta b, which is the Brewster angle, is equal to the arctangent of N2 over N1, where N2 is the index of refraction of the refracting medium, and N1 is the index of refraction of the incident medium. And I'm going to mention this here because I hope that everybody has been reading the textbook, and if you notice in the textbook, there are links to various videos. And if you have any difficulty with any of the math or the equations here, there's actually helpful videos that you can actually click on in the textbook that will bring you to those videos. Also, if you've watched those videos and you still have questions on the math, please do not hesitate to contact me and I will help you with the math part of it. So now we will discuss a little about the thermal properties of materials. Now, this is something that applies to all materials, not just here, but in this class we're going to be looking at the optical materials and also the mounts that hold them. And the reason I say that this applies to all materials is that every material has what's called a linear coefficient of thermal expansion, which is shown as alpha. And that's on the last column of this table here. And the units for that are times 10 to the minus 6 per degree Celsius. So every material is going to expand when the temperature rises, or it's going to contract as the temperature gets lower. So one of the things that we will look for in a material is that the alpha of the lens and the alpha of the mount should be relatively close if that's going to be subjected to a wide temperature change. Because if they contract and expand at different rates, it may cause distortion in the lens. The lens is going to try to grow at a different rate than the mount grows, and that could cause distortion. It could cause a change in the shape of that lens. The middle column in this that we look at is called thermal conductivity, and that tells us how good a conductor of heat a material is. So if you look at this table here, copper is given as a thermal conductivity of 238 joules per second per meter per degree Celsius, whereas glass is given as 0.8, and then silicon is given as 0.0013. So metals in general are very good conductors of heat. So if I apply heat to outside of a metal, the inside is going to get hot fairly quickly because they're such good conductors of heat. And that's why we use metals in things like cooking. And our pots and pans are generally made out of metal because they're good conductors of heat, right? The first column here actually shows us the melting point of different materials. So if we look at this table, we have copper with a melting point of 1083, silver with 961, and steel with 1535 degrees Celsius. As we go down the list to the crystals and glasses, flint glass has a melting point of 1425 degrees Celsius. Pyrex has a melting point of 1450. And then we go down to the bottom of this list, and silicon has a melting point of 1693. So that is important to us. If we're working in a very high temperature environment, we may have to make sure that we're nowhere near that melting point because we do not want our mount or our crystal or lens to melt. So these are things we should be looking at. I want to mention that my alpha, my coefficient of thermal expansion, is not only used here, but if you are an engineering science student, you will be seeing that again when we take statics or when we take strength of materials, because we do have to look at the temperature change that a system is seeing so that we could see whether it's going to expand or contract. So now we'll talk a little bit about mechanical properties of optical components. So a non-uniform stress on an optical component can result in distortion in the bulk medium and therefore its surface. So what does that mean? That means that our medium or our lens or our mirror are going to change shape, and if there's distortion in there, then it's not going to be reflecting or transmitting light in the same pattern that it did when there was no distortion. And that is unacceptable in many applications. So our relationship between the maximum stress, which will be given in pascals, and the geometry of a window is given by the following equation, where it's given as T, which is the window thickness, is equal to D, which is the unsupported diameter for a circular window, times 1.06 times delta P, which is the pressure difference between both sides of the window, divided by FA, which is the elastic limit of the material, raised to the 1/2 power, or we could write that as square root of delta P over FA. So as an example here, we have an example where we say a vacuum chamber is designed with 1 atmosphere of pressure outside. So 1 atmosphere is 1 times 10 to the 5th pascals, and 1 times 10 to the -8th torr of pressure. Inside, a circular window of diameter 0.25 meters made out of NaCl, which is sodium chloride, which has an Fa of 0.24 times 10 to the 6 pascals is used. The window is mounted on the chamber with a neoprene O-ring. Calculate the minimum thickness of the window if significant optical distortion is to be prevented. So I used that equation, which was 2.7, that says thickness is equal to D times 1.06 times delta P over FA raised to the 1/2 power. So substituting in for 0.25, which is the diameter, times 1.06 times 1 times 10 to the 5th minus 1.33 times 10 to the -6, which is the difference in pressure, divided by 0.24 times 10 to the 6th raised to the 1/2, I get 0.17 meters. So this window must be at least 17 centimeters thick to avoid distortion. Now, 17 centimeters is actually quite thick for a window. But the reason that we need that is because we have a very large pressure differential between the inside and the outside. And therefore, we need a window of this amount of thickness so we don't get distortion. So in this slide, we actually have a table that just gives us the elastic limits for some window materials. So that was the FA that was given in equation 2.7. So if we're given a problem with different materials, you could go to this table to look up what FA is. Now, the first column is actually the material. The middle column is FA in PSI, so that is in English units. And the column on the right side is FA in pascals times 10 to the 6. So that would be what we would use if the problem is given in metric units. This table here actually shows the solubility of some optical materials. The reason that we want to know that is because chemical damage can happen to optical elements if a chemical has the ability to either etch or dissolve the window materials. So example of this can be seen if, let's say, acetone touches plastic, right? So if you had a plastic lens and it was exposed to acetone, the plastic would start to dissolve, and so it would damage the lens. Similarly, water vapor actually can start to dissolve certain crystal windows, such as sodium chloride or sodium bromide. Glasses are not soluble in water. The solubilities in water of some of the crystalline and amorphous materials are shown in this table, and it's in terms of grams of material dissolved per 100 grams of water. So again, you could see if you have to look at whether it's insoluble or not, there are several materials here, like quartz, that's insoluble, right? So that would not get damaged by water because of that. So another thing that we have to look at is cost of optical components. Right? I mentioned earlier on, I asked, I don't know if anyone here has a hobby or has ever had a hobby in photography. I actually used to shoot a lot of pictures with 35mm cameras prior to digital cameras coming out. And I had a couple of different SLRs. And the one thing that you learned early on was that good quality lenses tended to cost more than not so good quality lenses. So there are factors that are going to determine how expensive or what the cost of a lens is. So I mentioned in the previous slide how acetone can affect plastic, but a lot of lenses nowadays are actually made out of plastic, and because they are actually quite cheap, so they are cheaper than a glass lens, and they could also be made in a mold, whereas glass lenses have to be ground down to their shape and size. So some of the factors that tell us how expensive a lens is going to be, or optical component is going to be, are its size. So again, think of that, the bigger that it is, the more material that it's using, so it's probably going to cost more. Similarly, the material, if it's made out of a more expensive material, it's going to cost us more. The surface curvature of the element, right? The accuracy of the flatness or curvature, the wavelength of light that's going to be transmitted, the type of coating on the surface, and the correction for aberrations, right? So these are all things that we have to look at. We're going to talk in this section about coatings, but you may see that if you go to buy optics, telling you that it's coated or it's non-coated, right? And so if it has a coating, it's going to be more expensive than a non-coating, and depending on the type of coating, it's going to be a different price depending on what the coating is. I'm going to end this video here, and I will continue with Module 2 in the next video. So what we will be discussing next are coatings, filters, mounts, and positioning equipment. Please check on Blackboard for all these videos, and I will be having the links as I have them posted also on YouTube. And please participate in our discussion forums. That is something you are graded on in this class, so please do that, and I hope that you enjoyed this lecture. Thank you.